Every year, over 4 million tons of steel wire rope are produced worldwide, and it's these thin, shining threads that hold up bridges, elevators, lifts, and ships. But what if I told you that before becoming a rope, every wire goes through real torture acid, flame, a press, and a tension capable of tearing steel apart? In this video, we'll show you how a piece of rough wire rod is born into a perfectly smooth metal thread, capable of withstanding thousands of tons of load. And at the end, you'll learn something that even the manufacturers themselves keep hidden. To create a steel cable capable of holding up a bridge hundreds of feet long, it all starts with the right alloy. Most often, it's carbon steel with a carbon content of around 0.6%, which provides both strength and elasticity. Sometimes chromium, nickel, or molybdenum are added for corrosion resistance and increased load capacity, especially for cables that need to work outdoors for decades. The metal is delivered to the factory in the form of huge steel slabs plates measuring 10 by 2 by half a foot and weighing up to 10 tons. They are heated in furnaces to 2,200 degrees Fahrenheit until the steel becomes plastic, almost like rubber. Then these red-hot billets are passed through rolling mills, turning them into long, thin rods with a diameter of approximately 0.25 inches. These are called wire rods. These wire rods are then cooled under controlled conditions, either in air or in special baths, so that the metal structure is dense and the internal stress is uniform. Next, a short storage stage. The metal is weighed, checked for hardness, flexibility, and the presence of microcracks. Only after this is each coil sent to the main section wire drawing, from which the future cables will be formed. After the steel wire rods have been cooled and checked for quality, they proceed to the wire drawing workshop. This process transforms the thick rods into thin but incredibly strong wire, which will become the foundation for bridge cables. Imagine a steel rod as thick as your finger, just off the billet. Its surface is rough, as if covered in a layer of sand or rust. This is scalar hard and brittle crust that appears during hot rolling. To prevent it from interfering with further metal processing, it needs to be removed. To do this, the wire rod is first lowered into a bath of acid solution, usually sulfuric or hydrochloric acid. In this solution, the scale seems to flake off the metal, just like old paint peels off after being treated with solvent. Then the wire is rinsed with a large amount of water under pressure to wash away all traces of acid and dirt. To the touch after this, the metal becomes smooth and cool, like a freshly polished stone. But that's not enough. Next, the wire goes through degreasing. It's submerged in special alkaline solutions that remove any oils that might have gotten onto the surface. And only then is the clean, smooth wire, shiny and dry, ready for the next stage drawing. Now the wire needs to be pulled through a hole smaller than the wire itself to stretch it out and make it thinner. But a thick end simply won't fit through. So, it's first sharpened. This process is called pointing. The wire is fixed in a special mechanism that resembles strong metal vice jaws. One end of it is inserted into a device similar to a small press or crusher, where the steel casing is gradually squeezed and stretched into a cone shape. This way, the wire is essentially machined into a pointed tip. Imagine a pencil sharpened at one end, only it's not graphite but cold, shiny metal. This sharpened end then easily fits into the first opening of the drawing machine, a small metal die. To the touch, such a sharpened part becomes thin, like a shoelace, but remains elastic and strong. This is where the drawing process begins, which will turn the rough wire rod into a thin steel wire for the cable. Picture a shining metal strand, about the thickness of a pencil, being gradually pulled through a series of metal rings. Each of these rings is a drawing die, looking like a coin with a hole in the middle, but made of super hard material, like tungsten carbide. The holes in each die are slightly smaller than the previous ones. The whole system is arranged in a line, like beads on a thread. The wire passes through the first ring, and it compresses it, stretches it, reducing its diameter. Next, the following ring, even smaller, and the same thing happens again. The entire wire is pulled by a powerful drawing machine, resembling giant toothed rollers or high traction rollers. It constantly pulls the wire forward, maintaining tension, and thus forcing it to pass through the dies. To the touch, after several passes, the wire becomes thinner and longer, like a silvery strand of hair. The surface is smooth, cool, with a clear metallic sheen. Importantly, this entire process happens without heating. The metal remains cold. That's why it's called cold drawing. The steel gets stronger in the process. Its structure becomes denser and more durable, like a muscle that's been trained. And so, ring after ring, an ordinary wire rod transforms into a high-precision wire for a future steel cable. The steel thread that has just passed through a series of drawing dies has become thinner and stronger, but at the same time stressed, like a stretched string with fatigue hidden inside. The metal has accumulated internal stresses, microscopic defects that reduce its ability to bend or stretch further without cracking. Yes, this wire has become brittle. To release this stress, the wire passes through a special thermal furnace. It's not visible from the outside. It's a long metal tunnel structure, inside which the temperature reaches over 1,000 degrees Fahrenheit. In such heat, resembling the middle of a bonfire, the wire slowly moves through the furnace, either lying on moving rollers or suspended. It gradually heats up to the required temperature and then slowly cools down. The whole process takes anywhere from a few minutes to an hour, depending on the thickness and grade of the steel. To the touch, the wire after this stage is just as smooth and shiny, but it no longer breaks. Inside the metal, its crystalline structure has rearranged itself. The stresses are relieved, plasticity is restored. Now it's ready for the next series of drawings, and it will become even thinner, stronger, and more durable. It's like giving your muscles time to recover before the next workout. In the final stage, the wire undergoes a final quality control, and this is definitely not a simple visual check. A long, almost continuous strand of shiny metal moves at a speed of tens of feet per second through the inspection unit. There, it's met by special sensors. This could be laser equipment that non-contact measures the wire's diameter with an accuracy of thousandths of an inch. Nearby devices that determine strength. A portion of the batch is selected for mechanical testing. The wire is clamped in hydraulic jaws and pulled until it breaks. This determines its tensile strength and braking load. If the wire holds up, it's ready for work at heights of hundreds of feet, supporting the weight of a car bridge. The surface is checked separately for microcracks, burrs, corrosion. High-resolution cameras or even eddy current testing are used here, which can see beneath the top layer of metal. And only the wire that has passed all these tests gets the green light. It will become part of a steel cable capable of withstanding years of loads and harsh weather. This is the final touch that guarantees what arrives at the construction site is reliable, like steel itself. After inspection, the quality wire is neatly wound onto large spools. The wire passes through guide rollers and tensioning mechanisms that ensure the coils lie tightly, but not too tightly. All this happens on high-speed winding machines. Spools come in different sizes. For thin wire, they might weigh hundreds of pounds. For thicker wire, a ton or more. Then these spools head to the next stage, the actual twisting into cables. But even before this, they are sometimes coated with an anti-corrosive compound or lubricant so the wire isn't damaged during storage and transport. Spools of wire are usually moved using forklifts, cranes, or special carts, because the weight of even one spool can reach several hundred pounds or more. Manual labor is out of the question here. Otherwise, the risk of injury would be too high. Every hour, over 100,000 airplanes take off around the world, but only one of them is a true ghost of the sky. It has no tail, leaves no trace on radars, and costs more than gold. The creation of the B-2 Spirit cost the United States $60 billion, and over 40,000 specialists from 600 companies worked on each unit. Its assembly took more than a year, with special hangars, laser-like surgical precision, and materials you can't buy in any store. But what this plane hides is still a secret, and if you watch until the end, you'll find out what it was really created for. The design of the B-2 Spirit strategic bomber began in 1979, when the Cold War was reaching its peak. It was then that the United States Department of Defense initiated the Advanced Technology Bomber program, with the goal of creating a new generation aircraft, capable of penetrating the most advanced Soviet air defense systems while remaining invisible to radars, and delivering nuclear or conventional weapons over intercontinental distances. Leading American aerospace corporations participated in the competition: Northrop, Boeing, Lockheed, and Rockwell. After a lengthy stage of development and testing, in October 1971, the Northrop-Boeing consortium was declared the winner. It was their project that received the designation B-2 and the name Spirit. Unlike previous strategic bombers, the B-2 was built on a unique flying wing design, which provided a minimal radar cross-section and significantly better flight characteristics. In the mid-1980s, the B-2's design had to be significantly changed. The mission profile was adapted for low-altitude flights with terrain following, which allowed for even more effective penetration of Soviet air defenses. This led to a 2-year delay in its first flight and an increase in the program's cost by $1 billion. By 1989, about $23 billion had been spent on the B-2's development, and even specialists from the Massachusetts Institute of Technology were involved in the work, assessing the aircraft's effectiveness under conditions of strict secrecy. The first public showing of the B-2 Spirit took place on November 22, 1988 at Plant 42 in Palmdale, California, which is where it was assembled. The first flight of the B-2 took place on July 17, 1989. Initially, the United States Air Force planned to order 132 aircraft, but after the end of the Cold War and the collapse of the USSR, as well as due to the extremely high cost, the series was reduced first to 75 and then to 21 units, including a prototype, 5 pre-production, and 15 production machines. Almost all B-2s received their own names in honor of American states, emphasizing their uniqueness and symbolic significance for the country. Thus, the B-2 Spirit became not only a technological breakthrough, but also a symbol of American military might at the turn of the 20th and 21st centuries. The production of the B-2 Spirit began not with the manufacturing of individual parts, but with the creation of a completely new industrial ecosystem capable of meeting the unique requirements for technology, materials, and assembly precision. The first and most important stage was the organization of the production base and the development of tools that did not exist before. After the design phase was completed, Northrop Grumman, as the prime contractor, invested over $1,200,000 in creating a specialized integrated composites center in Pico Rivera, California. For this, a former Ford auto plant was repurposed, turning it into one of the world's largest composite manufacturing centers. The production of the B-2 required the development of not only new materials, but also special tools, software, testing laboratories, and automated production systems. At this stage, the following were created: unique molds and tooling for forming large composite panels, automated lines for laying carbon fiber, computerized systems for cutting and shaping parts, and autoclaves for heat-treating composites at a temperature of about 350 degrees Fahrenheit and a pressure of 100 psi. The production of the B2 began with digital modeling. Engineers created three-dimensional CAD models and then directly manufactured production tools from them, bypassing traditional mock-ups. This allowed for achieving unprecedented accuracy. Even microscopic deviations could affect the aircraft's stealth characteristics. In parallel, a complex network of contractors and suppliers was formed. Over 6,000 companies and 40,000 workers from 46 states of the United States were involved in manufacturing components. Boeing was responsible for manufacturing the outer wing sections, Vought aircraft, for numerous composite elements, Hughes, for radar systems, and General Electric, for the engines. Only after the creation of this entire infrastructure did the direct manufacturing of parts, their processing, quality control, and subsequent assembly of the aircraft at the main plant in Palmdale, California, begin. Thus, the production of the B-2 Spirit started with large-scale preparation of the production environment, engineering innovations, and the development of new technologies, which made the creation of this unique aircraft possible. After the large-scale preparation of the production base, the creation of unique tools, and the establishment of material supply chains, the direct manufacturing process of the B-2 Spirit began. Events then unfolded in several key stages, each requiring engineering precision and strict coordination among thousands of specialists and hundreds of contractors. Manufacturing of the main fuselage and wing sections. The manufacturing of the main fuselage and wing sections of the B-2 Spirit began with the production of the world's largest composite aviation parts at that time. The central part with the crew cabin was manufactured by Northrop Grumman, while Boeing made the 65-foot-long outer wing sections and the 50-foot-long aft section. The slightest deviations could affect the B-2's radar cross-section. In total, over 10,000 composite components were manufactured for one aircraft, using the latest automation and quality control technologies of that time. The precision assembly of the B-2 Spirit is a true engineering feat that unfolded in huge hangars, specially created for this project. The assembly of the main sections took place on massive jigs, special platforms that occupied an area comparable to a football field. Here, hundreds of engineers, assemblers, and quality controllers worked simultaneously, each responsible for their narrow stage. Thanks to three-dimensional CAD modeling, all parts fit together perfectly. During assembly, laser measurement systems were used, which allowed for tracking accuracy down to thousandths of an inch. Even microscopic deviations could disrupt the aerodynamics or reduce the effectiveness of the stealth coating. Every joint seam was checked several times, and after connecting the sections, it was manually sealed with special materials to ensure airtightness and invisibility. The scale of the assembly was impressive. Just the central fuselage section required over 1,000 hours of labor, and the total assembly cycle for one aircraft took more than a year. All stages were accompanied by multi-level quality control, from geometry to electromagnetic compatibility. It was thanks to such attention to detail that the B-2 Spirit became a benchmark of precision and technological excellence in world aviation. After assembling the main structure, the integration of systems began. Electronics, hydraulics, fuel tanks, engines, flight control systems, radar complexes, and so on. Many subsystems had to be redesigned and adapted to the unique requirements of the stealth architecture. For example, placing the engines inside the wing to reduce infrared radiation. One of the most complex stages was the application of a multi-layer radar absorbent coating. The process took place in special hangars with a controlled microclimate. Each layer was applied by hand and then checked for defects that could increase radar cross-section. After completing the assembly and integration of all systems, the aircraft underwent multi-level tests. static and dynamic structural tests, checks of all systems operation, flight tests in various modes, and special radar cross-section tests. Any identified deficiencies were eliminated, and individual nodes could be reworked or even manufactured anew. After all tests were completed, the aircraft was officially handed over to the United States Air Force. In parallel, crews were trained, undergoing specialized training on simulators and in real flights. After the production of the B-2 Spirit ended in 2000, these unique aircraft did not become museum exhibits. On the contrary, they remain at the forefront of technological progress thanks to constant improvement. The U.S. Air Force is investing billions of dollars in modernizing each of the existing B-2s to ensure they meet current and future challenges. One of the main areas of modernization is updating the onboard control systems. Outdated analog instruments are gradually being replaced with modern digital interfaces, which increases reliability, convenience for the crew, and allows for the quick integration of new functions. The crew cabin has been equipped with multifunctional displays, and the flight control system has received new software that provides even greater stability and precision in controlling the flying wing.